I'm Colin Raby. Welcome to my 6-minute yap sesh on the history of nuclear technology, its origins, and its trajectory going forward. So, there's a quote. Oh, it's going to be annoying. There's a quote by Louis Pasteur that in the fields of observation, chance favors only the prepared mind. And that actually was the case for the very beginning of how we started to find out about radioactive rocks that led to nuclear technology, because Henri Becquerel, or however the French want to say that, was doing a lot of experiments with X-ray technology. And he had some uranium rocks that he was also experimenting with, especially the ones that glowed, because he was doing a lot of research in fluorescence. Fluorescence, basically things that glow. We used to put uranium in pottery and in dining stuff so that they glow at night. It's like a fancy, like, elitism thing. Yeah. So people used to, like, eat off those things, which is wild. But, so basically he was doing this research in fluorescence and X-rays, and he had this paper that he was X-raying to get images. And one night, very nonchalantly, he takes one of the uranium rocks and puts it on top of a piece of this photo paper he was doing and puts it in his drawer. Now this rock wasn't glowing, it was just a rock that he put on top of the paper in a drawer. And then the next morning, if we go to the next slide, you see, he saw that the paper was discolored. He was like, what's going on? This isn't one of the shiny rocks. Why is the paper all messed up? And so he wrote a paper on it, on the radioactive effects of uranium. People like Marie Curie and others started taking that research and doing even more research on it. And fast forward the next 20 years of research till we get to around Christmas in 1938, when they decided to give the world the gift of research. So within 1 year of World War II, Lies and Otto were doing research in Germany where they're bombarding elements with neutrons. And they realized through one of their experiments that they got more energy out than they put in. They're like, what? And what they ended up speculating is that the uranium nuclide actually lost mass, and if we go to the famous equation E equals mc squared, it loses a little bit of mass, produces energy. That mass really releases the energy. And they realized that they had something really weird going on. And so once they realized that they had this division of atoms happening, they're like, what are we going to call it? And so they did have some interest in biology. And so they decided, you know what? We're going to name this the same thing that we named cell division. Fission. So, next slide, please. So the fundamental of fission is essentially you take a uranium-235 atom, you bombard it with a nucleus, then that uranium-235 instantaneously becomes uranium-236, which splits into two other elements and releases three other neutrons. Those three other neutrons, if it's surrounded by uranium, can hit other uranium atoms and other uranium atoms. Until you get this chain reaction of energy being given off. And so anyway, so they do this research, and basically people around the world realize, hold up, this could be used for some interesting things, and giving off quite a bit of energy. And so they all realized it was an exophonic reaction. It gave off heat, lots of not only energy, but heat, and that compared to burning coal per pound of coal, it gives off like 200 million times as much energy. So yeah, these are some energetic rocks. But there's effectively only like two uses that people realize immediately from this research. The first use is that, oh yes, so the first, was there, was it after? I don't know, we can keep going. Anyways, so yeah, we can go. First was for making bombs. Hey, Manhattan Project, all of that. Now the big thing, I don't know how many people saw like the Oppenheimer movie, but one of the things I questioned after watching it is what was with the whole atmosphere ignition thing. I'd never heard of that. And so doing a little bit of research, what they were worried about is they were worried that the nitrogen in the air, so the air is about like 79% nitrogen, would literally, because of the heat of the explosion, fuse into magnesium, and then that would effectively create a mini sun in the atmosphere, and that would just continue fusing, and the entire atmosphere would just fuse and release a ton of heat. Fortunately, however, this was the equation that they used for that. They knew this variable, and they knew this variable, however, they had no idea what that variable was. So they had to take some guesses, and turns out that the main even though some of the bombs create enough energy, the main mechanism for transferring that energy to actual air atoms is through alpha radiation, actually hitting an air atom. And in general, it takes about 57 feet from explosion to actually hitting an air atom because it's not that dense. So you need like the ball of energy to be like 57 feet big of that dense energy. And it turns out for that, you would need a bomb that's about 100,000 times more powerful than the ones they were experimenting with at the time. Are we kind of close to that? Yes. I guess we just won't worry about that. But at the time, the thing you have to be worried about is the energy loss versus the energy in. So this was the curve of energy loss, this is the curve of energy in. Fortunately, the energy loss curve is above the energy produced curve, therefore it's losing more energy and it's not a self-sustaining reaction. So because of that, they felt safe to continue, even though the curve kind of got a little close at the end. They felt safe to continue, develop bomb. Bomb leads to fission energy that we have today, and that fission energy, now people are doing fusion energy and things like that. So it's a very interesting field, and I'm excited to see what we'll do next. Thank you.